Nuclear fission is the splitting of a heavy element's nucleus to form two new elements with smaller nuclei. One of the most important fission reactions is that of uranium-235, which is used in nuclear reactors and atomic weapons. The fission of uranium-235 is initiated when a neutron traveling with enough velocity collides with the uranium-235 nucleus. The collision produces uranium-236, which immediately splits into two lighter elements, such as krypton-91 and barium-142. The fission event also releases 3 neutrons and a large amount of energy. The 3 neutrons are capable of initiating more fission events if they encounter a uranium-235 nucleus. In a nuclear reactor, fission must be controlled in order to safely produce energy. The critical mass of a nuclear reaction is the point at which fission becomes self-sustaining because the number of neutrons produced by the fissioning particles is greater than the number of neutrons lost to the environment. In a nuclear reactor, reaching critical mass causes a meltdown, meaning that the nuclear reaction cannot be controlled and generates more heat than the reactor can handle. A nuclear power plant consists of 3 main parts: the reactor, the electric generation system, and the cooling system. In a nuclear reactor, fission must be controlled in order to maintain safety. This control is created by control rods, which can be raised and lowered into the reactor core, which controls the fuel rods. When a control rod is raised, fuel rods can directly interact with each other, increasing the heat of the reactor. When the rods are lowered, the neutrons can no longer pass between fuel rods and cause reactions, which causes the reactor to cool down. The reactor coolant is superheated by the fission reaction and is then cycled into a steam generator, where it conducts its heat into a separate cycle of water, which heats the water into steam. The reactor coolant is subsequently cooled and sent back into the reactor to continue its cycle. However, the steam then goes to the electric generation system. The steam is used to spin a turbine, which then generates electricity which can be sent away from the power plant. The steam is then cooled by yet another cycle of water, which brings cool water in from a lake or river and uses it to cool the steam down so that it can continue its cycle. The lake water gains this heat and has to be cooled, so it is then taken to a cooling tower. At the cooling tower, this water is cooled down or released as steam and continues its cooling cycle. The 3 separate systems of cooling ensure that none of the radioactivity from the reactor will escape.
One important concept in nuclear fission is the source of the energy released. So if we look at a nucleus, we see that there are nucleons that are held together by the nuclear strong force, which is stronger than the electrostatic forces attracting them to the electrons and repelling the other nucleons. So the nuclear binding energy is a measure of that force, and this is the energy released as neutrons and photons. So when a nucleus undergoes fission, it creates 2 daughter nuclei and neutrons. And since the binding energies of the daughter nuclei do not total the binding energy of the atom that undergoes fission, we know that this difference is the binding energy released, which comes in the form of neutrons and photons.
Another important concept in fission reactions is the mass defect of a reaction. In a reaction, the mass of the reactants will always be greater than the mass of the products. The difference between the 2 masses is known as the mass defect. This defect occurs because some of the binding energy of the fuel, which is represented as its mass, is released during this reaction.
So our practice problem states that in a nuclear reactor, there is 1 kilogram of uranium-235 which undergoes fission. Based on the reaction, neutron plus uranium-235 equals 3 neutrons plus barium-144 plus krypton-89 plus energy. So it asks us how much energy is released when uranium undergoes the reaction. So our first step in calculating the amount of energy released is to calculate the mass defect. And as we know, mass defect is equal to the mass of the reactants minus the mass of the products. So in this case, the mass of the reactants would be the mass of the neutron, which is 1.008665, plus uranium-235, which has a mass of 235.0439, minus the mass of the products, which in this case is 3 neutrons, plus barium-144, which has a mass of 143.9229, plus the mass of krypton, which has a mass of 88.9176. So this difference is equal to 0.18607 AMU. Now, having calculated the mass defect, we can calculate the amount of energy released using Einstein's mass equivalence equation, which is E equals delta mc squared. Now, we can plug in the mass defect for this delta m, and so we can use this value that we just found and multiply it by 931.5 mega electron volts per AMU. And this comes up to a total of 173.324 mega electron volts per reaction. Now, since this is the amount of energy released per reaction, we still have to convert this value into the amount of energy released in the reactor itself. So through this we use dimensional analysis, and so we know that there's 1,000 grams of uranium-235 that is being fissioned in the reaction, and we can convert this to moles using the molar mass of uranium-235, which is 235 grams per mole. And we know that according to Avogadro's constant, there are 6.02 times 10 to the 23 particles or atoms per mole. So this tells us that there are in the reactor 2.5617 times 10 to the 24 uranium-235 atoms. And from this we can use the amount of energy per reaction in order to calculate the amount of energy that's released in the reactor as a whole. So with that, we can find that there are 2.5617 times 10 to the 24 atoms multiplied by 173.324 mega electron volts per atom, which gives us 4.44 times 10 to the 26 mega electron volts that are released in this reaction.